Hey, Bio30. Welcome back. This is the last section that we're going to look at for digestion, nutrition, and that's where we're going to look at enzymes. So we've talked about carbohydrates and we've talked about proteins as well. Now, enzymes are a specific type of protein, but they're going to help us out with some of the reactions in our body. So they're chemical components. Essentially, they're catalysts, but they're biological catalysts. And if we talked about it before, it would have been very brief. Essentially, a catalyst is a component that can speed up the rate of a reaction. So think of any job you've had to do. Has there ever been something you can add to that job to make it go faster? I'll give you an example. For like say a hockey rink, and you need to run across the ice from one end of the ice to the other. I'm pretty sure we could all do that. But it'd be a lot easier if we had a pair of skates because now we have a hard edge that we can actually push ourselves along with. So you can see it's the same job, it just goes along a little bit faster, which would be nice. So in our body, we have enzymes. They are catalysts, they're just biological catalysts, and they're going to help us convert molecules from one form into another. We start off with what are called substrates. The enzyme is going to convert a substrate into what we call a product. Catalyst, just definition alone, is just a substance that speeds up or increases the reaction rate. Another interesting thing about catalysts and enzymes, though, is that they don't get used up. So they're there to help out. It's like those skates that we use to cross the ice. You still have them when you're done. You don't use them, right? So it's really nice that we have that. Whereas, I don't know, what's a different example would be you can't say the fuel in your car is an enzyme or catalyst because it gets burned up to give us that energy. A catalyst, on the other hand, is going to help us speed up our reaction. Enzymes are biological catalysts. So a catalyst and an enzyme are both the exact same thing. The enzyme is what we're going to find in our body. The catalyst could be anything. It could be something in our body. It could be something man-made. It just doesn't have to be a biological thing. There's a reactant. So in a chemical reaction, there's two sides. There is a product and a reactant. The reactants are what you start with. We call those a substrate. That's what we're starting with. And then what we end up with will be our products. All the enzymes that we use, remember, we can have globular or we can have the fibrous proteins. In particular, the globular proteins will always be the enzymes, or I should say it in the reverse. Enzymes will always be globular proteins. Every single enzyme, though, will be a different shape. It is specific to every single substrate. So they're incredibly specific. If there's a job that you need to speed up inside of your body, you need a very specific enzyme to do that work for you. There's a couple of different ideas of how this really works. There's an older theory. This is what I grew up learning about. Not grew up. This is what I learned about in school, which was a lock and key, the lock and key theory, where the enzymes and the substrates they work together as if there's a key opening a lock. The key has to fit into a specific shape in the substrate. Once that specific shape has been met, you can unlock the lock, and that is the actual reaction going forward. So your lock is the enzyme. The key is going to be the substrate. They have to fit perfectly in order for the reaction to work. Example here, if this is our enzyme, it has to fit perfectly onto our substrate, and that is going to allow our substrate to be split off into its products. Okay, if we take a look at it in an actual three-dimensional shape, you can see that there's a very specific enzyme. It has to go into a very specific pocket. That's where it fits in. And then finally, you have your enzyme substrate complex together. Now, there's a newer idea, newer understanding, which makes a little bit more sense. I know lock and key is a great analogy, but there's something called an induced fit, where the active site on the enzyme will actually change shape to fit the substrate a bit better. This helps explain some of these weird anomalies in our lock and key mechanism. So if we take a look, in the induced fit, you still have your enzyme and your substrate, but notice how the substrate doesn't fit into that enzyme very well. But if we take that enzyme and kind of bend it around, if we bend it around that substrate, it is actually going to fit. So it changes the bonds, it distorts the bonds, which adds a bit of stress to the bonds themselves, and that allows the reaction to go forwards. And here's an example of this little J-shaped molecule here. The substrate can fit into that gap. The J shape will curl around it and then split that substrate into the two products that we wanted. Okay, and just another image of what that is going to look like. So we've got sucrase, which is going to help us break apart sucrose. As you can see here, it's got the hexagon and the pentagon there. and it just fits in properly, and then that allows the two molecules to break apart. Another visual that we can look at here is our enzyme and a couple of substrates. In this case, there are two substrates that have to bond together, or it could go in the opposite direction where you have the enzyme splitting those two substrates apart. So it depends on which way you want to go. They can fuse the two substrates together, or they can split them apart. In this case, they're showing an example of two substrates fusing together. That fusion would happen normally. It's just it would might take a lot of time, might need a little bit of extra energy to work with. But if there's an enzyme that can speed up that reaction a lot better. Now, continuing on with the theories, we like to use this analogy of activation energy. So activation energy is not a theory. This is a real thing. Whenever you have any kind of reaction, you have to burn some sort of energy to start the reaction. So like when you start a car, for instance, it revs really high at the very start. That's because you are surpassing that activation energy. If you cannot surpass that activation energy, it's like a roller coaster. You go up, but then you come back down. Your reaction does not go forwards. However, if you have an enzyme that actually lowers the activation energy, so it lowers that hill and it makes it a lot easier for that reaction to go forwards. The enzyme, we say, is facilitating the reaction by lowering the amount of activation energy that we need. So a couple of examples here. Let's say we have a metal stick and I want you to break that metal stick. So I can give you the metal stick. You can take the stick and physically try to bend it. At some point, you're going to bend the stick. Sure, it's going to be a bent stick. And eventually, if you're strong enough, you're going to have a broken stick. And you can see that it's taking a lot of energy to actually break that stick. However, what if I gave you a clamp? Let's say I gave you a clamp instead of making you break it with your hands. We put it into the clamp. The clamp is going to bend the shape for you, and then it's going to break the stick for you. Well, you can see that it's going to, this is the blue line now. You can see that it takes a lot less energy. There might be a couple of different phases of activation energy, maybe one to get it into the clamp and one to actually break it. But regardless, your activation energy total is less than if you didn't have that clamp to begin with. So having that enzyme is really useful in speeding up and helping with that reaction going forwards. A couple of things that can affect how that enzyme is going to actually work with the various substrates that we have is, well, one of them is temperature. So if your temperature increases, that means that your enzyme action is going to increase as well. You have to be careful though, because remember, when we talked about proteins, temperature can denature a protein. So there's going to be what we call an optimal temperature, which is the best temperature for that enzyme to work. If you go beyond that temperature, the enzyme starts to break down, it gets denatured. If you're before that optimal temperature, then it's not working as efficiently as it can. We also have to worry about the pH. pH is the same idea, but pH can go in either direction. So there's typically what we call an optimal pH. If something is too basic, well, then it might be too easy to denature that protein. If it's too acidic, it might be too easy to denature that protein. So an example here, these black X's are two places where the protein would just denature. You can't get to that point if you're, say, too acidic or this yellow line is too basic. However, if you look at the red line here, this is the most optimal pH for certain enzymes. That might be useful for us. So salivary amylase, for example, very good at around 7, which is at our mouth. So amylase is fantastic in your mouth. However, it's very poor in your stomach. And we have different types of amylase in your lower intestine or your small intestine to um, help break down starches even in acidic environments. A couple of other things, it depends on how much of that enzyme you actually have. So how much enzyme and how much substrate do you have? If I have a lot of substrate, well, I can only react with the number of enzymes that are present. So you're going to cap off at a certain point. You're going to flatline. That's like, let's say our chairs in the classroom are the enzymes and you guys are the substrate. Well, we can only fill as many chairs, or we can only seat as many students as there are chairs in the room. So if I get more than, say, 28 students in this room, some of you are going to be left standing, and that's this flat line. I can only have a maximum of 28 full at the exact same time. However, if instead I change the amount of enzyme, well, what if I have a classroom full of unlimited chairs? Like, let's say we go into the gym and they have all those chairs out right now. Everyone can get a chair. Like, I can keep pumping people into that room and there's always going to be a chair. So the rate of the reaction increases no matter how many people or how much substrate I add to the situation. Couple other things, we have these guys called inhibitors. Inhibitors will also react with an enzyme, but they'll slow the enzyme down, or they will prevent the enzyme from reacting with the substrate. So competitive inhibition, for example, you have a molecule that bonds to the active site. By doing that, it stops the substrate from actually being able to react with that enzyme. You can also get non-competitive, where a molecule will bond to the enzyme, but in a different place, not the active site. But it's going to change the shape of the enzyme and change its chemistry. So now it's not going to work the same way with whatever substrate it was intended to work with. Got a couple of images where you can see that. Where in this top example here, we've got a reaction. There's a substrate. It comes into the enzyme. The enzyme is going to split that substrate into two products, and that's what should happen. But if there's inhibition, I might have a situation of non-competitive inhibition where an inhibitor sits into this active site. You can see it changes the shape of my enzyme. So yes, my substrate can still bond, but this enzyme is acting on this inhibitor right now, so it slows down this reaction. It doesn't actually speed it up the way that we wanted it to. The other example I have is competitive inhibition. That's the first example from the last slide, where your substrate wants to get into this enzyme, but if there's a competitor in the way, well, then it's a race. It's a 50-50 chance. One time the competitor gets in, one time the substrate gets in, it lowers your total product or your productivity. A couple of ways that you can do that. Last thing I want to show you is when we are naming the enzyme. So typically, not always, but if you have a very special enzyme, you won't do this. But for typical enzymes, if you discover an enzyme, you just end the name with the word ACE. If you add ACE to the end of a word, you're talking about an enzyme. So an example is if you're dealing with lipids, lipids are worked on by lipases. So it's lipids, the lip part, and you add ACE to the end of it. Proteins, we put proteases on the proteins to break them down. Another example I've got is, let's say you have acetylcholine, which is a neurotransmitter. Acetylcholine, the actual chemical name is acetylcholine ester. But if we're going to go with this name of adding ACE to the end of it, it's the same thing. We're just going to add ACE to the end of our word. We end up with acetylcholinesterase. And that's actually the enzyme that works on acetylcholine ester. So just a couple of examples of how you can name enzymes. If you ever see the ACE, you're looking at an enzyme. Anyways, that's going to bring us to the end of enzymes. So it's not a very long presentation. I know there's not a lot of extra information that we need to go over, but just so you have an idea of what those are, and that should cover you for digestion and nutrition. So I'm going to leave it here for now. Hopefully you had a chance to work on your practice. If not, you want to get on that, because we'll look at some assessments shortly. Anyways, hope you're having a good day, and I'll see you guys later on, hopefully in class.